Welcome to No Kite. In this video, we will discuss about top 10 most dangerous engineering mistakes. Let's start. Engineering mistakes can vary in scale and impact, and it's important to learn from them to improve future projects. Here are 10 significant engineering mistakes. 10. Vasa Warship A1628. The Vasa was commissioned by King Gustavus Adolphus of Sweden and was built between 1626 and 1628 in Stockholm. It was intended to be a powerful warship to symbolize Sweden's military might and prestige. The ship was designed by Henrik Aberration, a Dutch shipbuilder. Specifications are as follows: length of approximately 69 meters at 126 feet, width of approximately 11.7 meters at 38 feet, displacement of about 1,200 tons, armament of 60 for bronze cannons onto gun decks. The Vasa made its maiden voyage on August 10, 1628. However, shortly after setting sail, the ship encountered a strong gust of wind and heeled over. Water started to enter through the open gun ports, and the ship sank in Stockholm's harbor. This tragic event resulted in the loss of around 30 lives. The Vasa was carefully restored and is now housed in the Vasa Museum of Vasamuseum in Stockholm, Sweden. 9. Hubble Space Telescope Spherical Aberration in 1990. The Hubble Space Telescope HOSTO was launched on April 24, 1990. With the promise of providing unprecedented views of the universe. However, shortly after its launch, it became apparent that the telescope's primary mirror suffered from a significant flaw known as spherical aberration. Spherical aberration is an optical imperfection that occurs when the surface of a lens or mirror is not perfectly shaped, resulting in the light being focused at different points, causing blurring and degradation of image quality. In the case of the Hubble Space Telescope, the primary mirror was ground to the wrong shape, causing light to be improperly focused and leading to blurry images. The flaw in the Hubble's mirror was a deviation from the intended parabolic shape by a tiny amount, just about to point to micrometers, but this small error had a significant impact on the telescope's performance. Images produced by the HUS were not as sharp as they were expected to be, and the telescope was not living up to its scientific potential. To address this issue, a series of corrective measures were taken. The most significant of these was a space shuttle mission, STNCU-61, a space shuttle endeavor, which was launched on December 2, 1993. During this mission, a team of astronauts installed corrective optics in the form of the Corrective Optics Space Telescope Axial Replacement, a COSTAR, and other instruments during a series of 5 spacewalks. COSTAR was essentially a corrective optics package that acted as glasses for the telescope, compensating for the spherical aberration and allowing the Hubble Space Telescope to capture much sharper and clearer images than before. After this successful repair, the Hubble Space Telescope went on to become one of the most productive and celebrated scientific instruments in the field of astronomy, providing remarkable insights and breathtaking images of the cosmos. 8. Ford Pinto fuel tank design in the 1970s. The Ford Pinto is infamous for its fuel tank design in the 1970s, which was associated with a significant safety concern. The design flaw involved the placement of the fuel tank in a vulnerable location, making the vehicle susceptible to fires and explosions in rear-end collisions. The Pinto's fuel tank was positioned in a way that, in the event of a rear-end collision, the fuel filler neck could be pushed into the tank, causing the tank to rupture and potentially ignite. This flaw was exacerbated by the lack of adequate reinforcement or protective shielding for the fuel tank, making the Pinto more dangerous in certain collision scenarios. The safety issue gained widespread attention after a series of investigative reports and lawsuits. Ford was accused of being aware of the safety concerns but choosing not to address them due to cost considerations. It was revealed that Ford conducted a cost-benefit analysis weighing the expense of recalling and modifying the Pinto against potential legal settlements resulting from accidents. The Ford Pinto case serves as a cautionary example of the importance of prioritizing safety in product design and development and the ethical considerations involved in decision-making processes, especially when human lives are at stake. The episode contributed to increased scrutiny of corporate practices and regulations related to automobile safety. 7. Millennium Tower, San Francisco, a 2009 present. The Millennium Tower is a residential skyscraper located in San Francisco, California, completed in 2009. It stands at 58 stories tall and is situated in the south of Market Asoma neighborhood, close to the San Francisco Bay. The tower was designed by the architectural firm Handel Architects Lept. However, the Millennium Tower has gained significant attention and controversy due to an unexpected issue related to its structural integrity and foundation settlement. The building has been sinking and tilting since shortly after its completion. The settlement issue became publicly known in 2016 when it was revealed that the building had sunk approximately 16 inches of 41 km and had tilted about 2 inches of 5.1 km at the base. The sinking and tilting were attributed to the building's foundation system, which was supported by concrete friction piles rather than the traditional steel piles driven deep into bedrock. The residents of the Millennium Tower, who had paid high prices for their luxury condominiums, expressed concerns about safety, property values, and potential health hazards due to the settlement and tilting. Various experts and engineers have been involved in assessing the situation and proposing potential solutions to stabilize the building. Efforts to address the settlement issue have included retrofitting and implementing a plan to install additional piles to reinforce the foundation. Additionally, there have been legal battles between the homeowners, the developer, and other parties to determine responsibility and potential compensation for the affected residents. The Millennium Tower situation remains an ongoing and complex issue in San Francisco, prompting discussions about building regulations, engineering practices, and the responsibility of developers and relevant authorities in ensuring the safety and stability of high-rise structures. 6. St. Francis Dam failure. California in 1928. The St. Francis Dam failure was a catastrophic disaster that occurred on March 13, 1928, in the state of California, United States. The St. Francis Dam, part of the Los Angeles Aqueduct System, was designed and built under the supervision of William Mulholland, was also the chief engineer of the Los Angeles Department of Water and Power. The dam was located in San Francisco Canyon, about 40 miles northwest of Los Angeles. It stood at a height of approximately 185 feet. A 56-meter zone was intended to provide water storage for the growing population of Los Angeles. On the night of March 12, 1928, the dam catastrophically failed, sending an enormous wall of water and debris downstream into the Santa Clara River Valley. The failure unleashed an estimated 12.4 billion gallons of 47 million cubic meters of water, causing immense destruction and loss of life. The flooding resulting from the dam failure traveled over 50 miles 80 kilometers out and reached the Pacific Ocean. Entire communities were devastated, with an estimated death toll ranging from 400 to 600 people. Homes, farms, bridges, and infrastructure were washed away or severely damaged. The exact cause of the failure was attributed to a variety of factors, including inadequate geological surveys and flawed engineering decisions. The construction materials and techniques used were also considered subpar. Additionally, the dam was built on a geologically unstable foundation, which contributed to its failure. The St. Francis Dam failure remains one of the deadliest civil engineering disasters in U.S. history and led to significant changes in dam safety regulations and engineering practices. It served as a tragic reminder of the importance of rigorous engineering, geological assessment, and thorough inspections in the design and construction of critical infrastructure. 5. Tacoma Narrows Bridge Collapse, Washington, USA in 1940. The Tacoma Narrows Bridge collapse was a dramatic engineering failure that occurred on November 7, 1940 in Tacoma, Washington, USA. The collapse involved the Tacoma Narrows Bridge, which spanned the Tacoma Narrows Strait of Puget Sound. The original Tacoma Narrows Bridge, often referred to as Galloping Journey due to its characteristic undulating movements, was a suspension bridge designed by engineer Leon Moisfeed. It featured a narrow and flexible deck, making it vulnerable to aerodynamic forces, especially during windy conditions. On the day of the collapse, strong winds were blowing through the Tacoma Narrows at speeds of approximately 40 to 45 miles per hour, 64 to 72 kilometers per hour. The wind-induced forces, combined with the bridge's design flaws and natural frequency, set off a series of destructive oscillations. As the winds intensified, the bridge began to oscillate in a twisting, undulating manner. The movements quickly escalated, and the deck's motion became severe, resembling a wave-like pattern. This eventually caused structural failure, and the bridge collapsed into the Tacoma Narrows Strait within a few hours of the onset of the destructive oscillation. Thankfully, no human casualties occurred during the collapse, as a dog named Tubby was the only fatality. However, the collapse was a significant engineering failure that highlighted the importance of understanding aerodynamics, structural design, and the need to consider external factors like wind forces during construction. The lessons learned from the Tacoma Narrows Bridge collapse significantly influenced subsequent bridge design and engineering, particularly in the understanding and mitigation of aerodynamic forces on long-span structures. The incident had a lasting impact on the field of engineering and became a case study taught to engineering students worldwide. 4. Hyatt Regency Walkway collapse, Kansas City, Missouri, USA, 1981. The Hyatt Regency Walkway collapse was a tragic engineering disaster that occurred on July 17, 1981, at the Hyatt Regency Hotel in Kansas City, Missouri, USA. The collapse involved the atrium walkways, resulting in a significant loss of life and injuries. The Hyatt Regency Hotel featured a unique design with suspended walkways spanning the atrium, allowing guests to access different levels of the building. However, during a crowded event in the hotel's atrium, the fourth-floor walkway suddenly collapsed directly onto the second-floor walkway below. This catastrophic failure caused the loss of 114 lives and injured over 200 people. The collapse was attributed to a design flaw in the walkway system. The original design called for a continuous set of rods to support the walkways, but this design was changed during construction to a more cost-effective design using a single set of rods. The change doubled the load on the connection points, making them unable to sustain the weight of the suspended walkways in the crowd. The tragic event led to a significant reevaluation of engineering practices, building codes, and regulations related to structural design and construction. Lessons learned from the Hyatt Regency Walkway collapse emphasized the importance of adhering to approved designs, thoroughly reviewing engineering changes, conducting proper structural analysis, and ensuring public safety in the design and construction of structures. This disaster remains a stark reminder of the responsibility that engineers and architects have in upholding the highest standards of safety and integrity in their designs, as well as the devastating consequences that can occur when those standards are compromised. Free Deepwater Horizon oil spill, Gulf of Mexico, USA, 2010. The Deepwater Horizon oil spill, often referred to as the BP oil spill, was a major environmental disaster that occurred in the Gulf of Mexico in 2010. The incident involved a blowout on the Deepwater Horizon offshore drilling rig, which was being operated by Transocean and owned by BP or British Petroleum. On April 20, 2010, a well control failure resulted in a blowout, causing a catastrophic explosion and fire on the drilling rig. 11 crew members lost their lives in the initial explosion. The blowout preventer, a critical safety device meant to contain such incidents, also failed to operate as expected. Following the blowout, the wellhead on the seabed began to release a massive amount of oil and natural gas into the Gulf of Mexico. The oil spill became one of the largest environmental disasters in U.S. history, with estimates suggesting that millions of barrels of oil were released into the Gulf over a period of 87 days before the well was successfully capped. The spill had devastating consequences on marine and coastal ecosystems, wildlife, and the fishing and tourism industries in the affected regions. Efforts were made to contain the oil, clean up the affected areas, and mitigate the environmental damage. It also prompted a significant overhaul of offshore drilling regulations and oversight in the United States. The Deepwater Horizon oil spill raised awareness about the risks associated with offshore drilling and emphasized the need for improved safety measures, emergency response protocols, and a greater focus on environmental protection and sustainable practices in the oil and gas industry. 2. Space Shuttle Challenger Disaster, NASA, USA. In 1980s, the Space Shuttle Challenger disaster was a tragic incident that occurred on January 28, 1986, when the NASA Space Shuttle Orbiter Challenger of 1990 broke apart 73 seconds into its flight, resulting in the deaths of all 7 crew members on board. The crew of the Challenger included Francis R. Scobie, a commander, Michael J. Smith, a pilot, Ronald McNair, a mission specialist, Ellison Wanazuka, a mission specialist, Judith Resnick, a mission specialist, Gregory Jarvis, a payload specialist, and Krista McAuliffe, a payload specialist and first private citizen selected to fly in space. The disaster was caused by the failure of an O-ring seal in its right solid rocket booster. The O-ring failure caused a breach in the SARB joint it sealed, allowing pressurized burning gas from within the solid rocket motor to reach the outside and impinge upon the adjacent SARB field joint attachment hardware and external fuel tank. Aerodynamic forces rapidly broke the vehicle apart. The Challenger disaster had a profound impact on the space program, leading to a suspension of the Space Shuttle program and a comprehensive review and redesign of the shuttle's boosters. It also resulted in a reevaluation of NASA's safety procedures and communication protocols. This tragic event highlighted the risks and challenges associated with human spaceflight and served as a somber reminder of the importance of rigorous engineering, safety measures, and proper communication in the space exploration industry. It remains a critical case study in engineering ethics and decision-making for engineering professionals. 1. Chernobyl nuclear disaster, Ukraine. The then USSR, 1986. Chernobyl nuclear disaster was a catastrophic nuclear accident that occurred on April 26, 1986, at the Chernobyl nuclear power plant in Pripyat, Ukrainian Senior, which was then part of the Soviet Union of present-day Ukraine. During the safety test in Reactor 4 of the power plant, an unexpected power surge and subsequent explosion resulted in a fire that released a significant amount of radioactive particles and gases into the atmosphere. The explosion and ensuing fire released more than 10 times the radioactive fallout of the atomic bombs dropped on Hiroshima and Nagasaki. It had severe immediate and long-term consequences, including a human casualties. Immediate casualties included plant workers who died from the explosion and firefighters who battled the blaze. The long-term effects of radiation exposure led to numerous additional deaths, cancers, and health problems in the affected population. Evacuation and contamination of the immediate area around the power plant was evacuated, and a large exclusion zone was established. The radioactive fallout contaminated large parts of Europe, affecting food, water, and soil. Environmental impact of the environment around Chernobyl was heavily contaminated. Flora and fauna were significantly affected, and the region remained contaminated for an extended period. The nearby Pripyat River was contaminated, affecting water resources and aquatic life. Sarcophagus and containment to contain the radiation and prevent further release of radioactive materials. A massive containment structure called the sarcophagus was constructed over the destroyed reactor. In recent years, a new, more durable containment structure known as the new safe confinement was placed over the original sarcophagus to provide additional protection and structural stability. The Chernobyl disaster remains one of the most severe nuclear accidents in history, serving as a tragic reminder of the potential consequences of nuclear accidents and the importance of strict safety measures in the operation of nuclear facilities. Learning from these engineering mistakes is crucial to prevent similar errors in future projects and ensure the safety and reliability of structures and systems. Engineers continually strive to improve design, construction, and maintenance practices to mitigate potential risks and errors. Thank you for watching No Kite. Please subscribe our channel to see more informative content.